还有 present 的是跟管老师的这个一起合作的工作，那我们欢迎他。
Good afternoon, everybody, and thanks CTS give me a chance to present our work. Generation and stabilization of three-party qubit system. In a circuit QED, this QED is a superconducting system, and the qubit is, of course, the superconducting qubit. And we realize this scheme use feedback control. In the past, W-state is which is a three-party entangled state has been done in several systems. For example, the first article is in the NMR system, recurrent magnetic resonance system, and with photons, ions, and the last two is the superconductor systems. The general W-state use a sequence of pulses. You can, they are in a isolate. Let's assume they are in an isolate system, and we can realize the entangled state use a sequence of unitary dynamics. But here we have a different approach. We generate the W-state assessment by measurement. That means because when we adopt the measurement and the quantum state will collapse on one of the eigenstate of the measurement operate. So the scheme will be, I feel it will be simpler, and the time only depends on the feedback control strength and the measurement strength. However, a quantum system not easy, typically has its surroundings. Other quantum objects coupled with this with the interesting system. So we have to consider the system and the bed. The bed here, the many unknown quantum objects. We have to consider system and bed together to be a huge quantum space in a quantum system in a Hilbert space. But because we want to focus on the system interest system only, so we would eliminate the bed and remain the information of the system only. So typically we can one of the methods to describe this open system, we use a mathematical equation to describe the dynamics of these open systems. And rho here is a reduced matrix because the information of the bed is eliminated. And L here is a super operator acting on a reduced density matrix. And with respect to the T, here is the current time, and T prime is the past, which is less than T. The green equation is a general form of the mathematical equation, but it usually not easy to be solved because we can find rho and L here as T prime and routine. And however, it is not, even we want to obtain an analytic form, and this is not easy to obtain an analytic form. But in some special cases, we can solve this exactly, and it will become this Yale equation. And this equation, we call it as a canonical form, because we find the information of history is packaged in the L. I mean, it means the history, the system evolved only influenced by the history of the bed only. So here L here it already include a description of the bed, and the bed usually can be described by the time correlation function or bed time correlation function. So in most cases, we also can solve this problem perspectively and obtain a time conversion. And technical conversion is approximation. This approximation means we just take low t to low t prime to low t, and we can update the time conversion process. And if we take a Markovian approximation here, means the correlation function, the best time correlation function is a delta function, and that means we don't care about the history of the best at all, and we find that the system will only, the L here is only time dependent, and the decoherence of the systems will be proportion of a certain rate. We call it as a decoherence rate. The decoherence is a fact from the we can solve like this. The decoherence comes from because we can think the system and bus is a huge system, and finally there will be in an equilibrium state of the system and bus together. But however, we only read the information from system only. So the system here we have the information, the system we have is only can be declared by a mixed state. It is no longer be pure. The mixed state here means the system should be described by a mixture of several pure states with some probability. And so this is the schematic of our work. A microwave current passes through a waveguide, and the waveguide is the center of the center line of this picture. And this blue I mean the picture in blue, the boxes in blue are the superconducting substrate, and the two capacitors are cut the transmission line restaurant to be a cavity, and so there is a cavity, and between these two capacitors, and it is formed as an open side cavity. There are three small boxes in the bottom, and these are artificial atoms. We usually is a Cooper boxes, is a charge qubit, and is a two-level system here. So we read these two-level systems by coupled to a common cavity field and read the field transmitted from the cavity here and use a mixture to mix the field transmitted from the cavity, and there is a strong local offset. And this strong local offset is the same source from the crop field, I mean the cavity field, to become, there's some idea like the interference to read the phase shift of the transmitted field. So after we read the field, we can estimate the state of the qubit and give the feedback control. And we use this current we measured to give some quantum estimation to obtain the information of our qubits and give the feedback control to deliver the qubits onto the state we want. So in this work, we want to not only generate but stabilize this. Is the W state. The W state is, for simply because it's a numerical simulation, so we only consider a three-party state. And this is here. This is W state with a single excited state, and is an entangled state. So, as I told before in the last slide, we put the artificial atoms inside cavity, so it can be studied for simulation by just Cummings models. So the first term here, A and A dagger, is the creation and annihilation bosonic operator to describe the field in the cavity. And omega C is cavity frequency referring to a driving frequency. I mean, it's cavity frequency and referring to a driving frequency because there's a driving field with the amplitude epsilon. And this is in the rotating frame of a driving field. The qubit is described by Pauli matrix here. So sigma z here is a two-level operator, and the energy difference is capital omega I, and they couple to the common cavity field with coupling strength Gi. Of course, this is an open system, so the cavity, the atom, artificial atom, there is a decay of that artificial atom with some decay rate. So you just use H gamma to present the decay and H kappa to mean the photon or the field emitted from the cavity. So this is so we to monitor the qubit, we choose the driving frequency is resonant to cavity frequency, because as when we and the frequency should be larger from the qubit frequency because we don't want the qubit driven by the cavity field. So in the dispersive limit, I mean the tuning is much larger than the couple. So we can use this canonic transformation, and just Cummings Hamiltonian will become this purple equation. Here I missed the driving term, and this should be a driving term here, because I missed it. because after this transformation, we find the couple term. The couple term in this yellow. In yellow will become the term in the red box, inside the red box, and this means the cavity field will be a frequency shift, depends on the state of the qubit. For example, if the qubit is on the excited state, and sigma z will give us a plus, and the cavity frequency will become omega z plus g squared over delta. And otherwise, when the qubit is on the ground state, and it will become omega z minus g squared over delta. So this is the reason we will choose the cavity frequency resonate to the driving frequency, because in this condition, omega scale should be 0. So we can monitor the frequency of the field transmitted from the cavity, a positive or negative, and to determine the qubit is on the excited state or on ground state.
再5分钟。
Okay, so this is a homodynamic measurement because we have the phase shift measurement, so we use a homodynamic measurement to mix the output and output signal and subtract after the detector. And this measurement scheme can be simulated by the so-called stochastic measurements. Stochastic method equations, and W here is the white noise due to the short noise of the detectors. So use the homodynamic measurement scheme, we can read the field in the fast space. Here, I mean, this is the here is the fast space, and this is an in-phase space, and there's a spin set space and contractor components. And the red here, it should be the reference line of the local offset. This means if we choose the the phase of local offset to be the phase to be parallel to the x-axis, there will be two measurement outcomes, and if we perpendicular to the axis and level a single outcome, and this is what to differentiate the upstate or downstate or not. And if we can differentiate the ground state or excited state, and the system will be broken by a measurement. If not, the system will be conserved. So we use this So you use the idea to measure the state until the entangled state, so and guarantee the W state cannot be destroyed, but it can recognize from the other state. So we also eliminate the cavity field by the here called Coulomb type transformation, because because it is a longitudinal limit, so the cavity field remain on the steady state of the coherent state, and this coherent is respect to the project operator here. The project operator project the qubits on the excited ground state or other. I mean the ground state of this and mixture of the ground state. cross-site will be excited in each qubit. And finally, we can obtain the master equation in this form. This form is the first term is the self-emission, the evolution of the qubit when the system is not affected by the environment. And the second term here is the decay of the atom. And the third term is the decay due to the cavity field, and we call it the Purcell effect. And the fourth term is the effect from the measurement. So the effect in these three terms will break the coherent dynamics of the qubit. So we choose the dispersive coupling here, which we choose this coupling here is equal, and this it can help us to preserve the state of the W state, because if we want to generalize and spell out the W state, we should not recognize these three states. If we replace that states, and the W state should be read by the measurement. So we should choose an operator which the outcome should be the same in these three steps. So we use the feedback control, and I'm sorry I did not catch the time proper. And so finally, we use the feedback control to generate the W state. We can from this general initial state to reach a much better fidelity. And we also have distinguish some parameter in a different. This game, even when the decay rate is not equal, and we can, it's not bad. I mean, the generate to the entangled state is not bad. And thank you here.
Thank you. Questions? I have a question. Has any group tried to build a device that you propose?
Yes. But the device that is proposed by the Yale groups or WORAD this is also the author in the lesser reference. They replace something in this group provide this device, but they did not use a feedback control scheme. No. So I remember Martini is in some also other group they also use a similar device. There's also superconducting fast, and now let's compose the feedback control scheme and open optimal control scheme together, and to test our work.
I hope your result can be tested soon. Okay. All right. More questions? Okay. Let's think. Yun, 你是上宇 again. Okay, next talk will be given by 谢晓峰。李晓峰，小。